Hi everyone, today we're going to study Cramer's rule for 2 by 2 linear system of equations. We shall see how the determinant can be used to solve a system of linear equations. By definition, a system of linear equations is said to be consistent if the system has at least one solution. And the system is said to be inconsistent if no solution exists. Here we have three examples. The first example, x plus y equals 5 and x minus y equals 3. We can solve for the values x and y, and we will find that x equals 4 and y equals 1. Here we say that there is a unique solution. Therefore, this system is consistent. If we're going to graph the two equations, we will find that these are two intersecting lines. Now, example 2. 2x plus 3y equals 8. 4x plus 6y equals 16. If we solve for x and y, we will see that x equals k and y equals 8 minus 2k over 3. We can put any value for k. Then another value will come for the y, which means we have infinite number of solutions. But then this is called consistent system. If we're going to graph the two equations here, we will see that we have two coincident lines. Example C, 2x plus 3y equals 8, 4x plus 6y equals 15. If we solve for x and y, we will find that there is no solution. Because of that, we will call this system as inconsistent. If we're going to graph the two equations, we will see that these are two parallel lines. Let's go to Cramer's rule. If A is a non-singular n by n matrix, that is, determinant of A is not equal to 0, then the linear system capital A times capital X equals capital B of n linear equations with n unknowns, x sub 1, x sub 2, x sub 3 up to x sub n has unique solution. The solution is x sub 1 equals determinant of a sub 1 over determinant of a. X sub 2 equals determinant of a sub 2 over determinant of a. Up to x sub n is equal to determinant of a sub n all over determinant of a, where a sub j is the matrix obtained by replacing the entries in the jth column of A by the entries in the matrix B, or the matrix of constants. Take note that Cramer's rule does not apply if determinant of A is equal to 0. Let's go now to Cramer's rule of 2 by 2 system. Consider the linear system of equations a sub 1 x plus b sub 1 y equals d sub 1, a sub 2 x plus b sub 2 y equals d sub 2, where x and y are unknowns. This system can be written as in matrix form. We have the matrix for the constants a sub 1, b sub 1, a sub 2, b sub 2. Then we have the matrix for the variables, the column matrix xy equals, we have the matrix for the constants. This is the column matrix d sub 1, d sub 2. And this is the same with ax equals b. A here is the matrix for the constants. X is the matrix for the variables. B is the matrix for the constants. With determinant of A not equal to 0, we have now this formula to get the values of the unknowns. For the x, this is equal to determinant of A sub 1 over determinant of A. And the variable y is equal to determinant of A sub 2 over determinant of A. Remember, A sub 1 or the matrix A sub 1 is equal to D sub 1, B sub 1, D sub 2, B sub 2. And the matrix A sub 2 is equal to A sub 1, D sub 1, A sub 2, D sub 2 respectively. This is our working formula. Example, use Cramer's rule to solve the following system of linear equations. 5x plus 2y equals 4, 7x plus 3y equals 5. Let us write the corresponding matrices. Matrix A equals 5, 2, 7, 3 respectively. Matrix X equals the column matrix XY. Matrix B equals the column matrix of constants 4, 5 respectively. Let us compute the determinant of A. So this is 5 times 3, 15, minus 7 times 2, 14. 15 minus 14 is equal to 1, and we say that, of course, this is not equal to 0. Therefore, the values of x and y are defined. First, let us compute for the x. This is equal to determinant of A sub 1 over determinant of A. First, let us copy the matrix A in the denominator. It will be like this. And for the matrix A sub 1, we will have like this. It is almost the same with the matrix A except the first column. And that is, we replaced by the constants here. Then let us evaluate the corresponding determinants. 4 times 3 is 12, minus 5 times 2 is 10. All over 5 times 3, 15, 7 times 2, 14. Simplifying, we have now 2 over 1 or equal to 2. This is the value of x. For variable y, this is equal to determinant of A sub 2 over determinant of A. First thing is, we can copy the matrix of A here. And for the A sub 2 matrix, we have like this. It is almost the same with the matrix A except the column 2. We will replace this by the elements of matrix B. Then let us evaluate the corresponding determinants. 5 times 5, 25, minus 7 times 4, 28. Over 5 times 3 is 15, minus 7 times 2, 14. We can simplify further into negative 3 over 1 or negative 3. This is the value of y. Today, we're going to study Cramer's rule for 3 by 3 system. Consider the linear system of equations. Here, the x, y, and z are unknowns. This system can be written in matrix form. So we have here three matrices. The first matrix corresponds to the coefficients of the variables. The second matrix is the column matrix for the variables x, y, and z. Equals, the third matrix is the matrix for the constants. D sub 1, D sub 2, D sub 3. And simply we can write like this. Capital A times capital X equals capital B. Capital A corresponds to the matrix for the coefficients. Capital X corresponds to the matrix of the variables. Matrix B corresponds to the matrix of the constants. When we check that the determinant of A is not equal to 0, then we say that the system has unique solution. This is now our formula for the variables. Variable x is equal to determinant of A sub 1 all over determinant of A. Variable y equals determinant of A sub 2 over determinant of A. Variable z equals determinant of A sub 3 over determinant of A. Looking at the formula for the x, we need here matrix A sub 1. And this will be that matrix. This is similar to our matrix A, except that the elements of the first column is replaced by the constants respectively. Now, for the formula of y, we need matrix A sub 2. This is the matrix A sub 2. This is similar with the matrix A, except that the second column is replaced by the elements of the constants, respectively. For the formula for z, we need matrix A sub 3. And this is the A sub 3 matrix. This is similar to our matrix A, except the third column is replaced by the elements of the constants. This is now our working formula. Let's see this example. Use Cramer's rule to solve the following system of linear equations. Our first step is to collect the corresponding matrices. Matrix A will be the coefficients of the variables. So we have 1, negative 1, 1. 1, 1, 1. 1, negative 1, 2, respectively. For the matrix X, this is equal to the column matrix X, Y, Z. Matrix B is equal to the column matrix for the constants 4, 2, 4, respectively. Then let us check if the determinant of A is not equal to 0. Using our diagonals method, we will see that this is equal to 2 plus negative 1 plus negative 1 minus positive 1 minus negative 1 minus negative 2. Then we simplify by 2 minus 1 minus 1 minus 1 plus 1 plus 2. And the final sum will be positive 2. We can see that this is not equal to 0. Therefore, the system has unique solution. Let's begin with the variable x. This is equal to determinant of A sub 1 over determinant of A. We can start by copying the matrix A in the denominator. Then the numerator becomes like this. This is our matrix A sub 1. It is similar to our matrix A except that the first column is replaced by the elements of matrix B. Then let us evaluate the determinants respectively. In our denominator, we solved this a while ago, and we can write the answer here. For the numerator, it becomes like this. We will use the diagonals method. The values will be 8 plus -4 plus -2 minus 4 minus -4 minus -4. We simplify our numerator to be 8 minus 4 minus 2 minus 4 plus 4 plus 4. And the final answer in the numerator is 6. We divide this by 2. The answer is 3. This is the value of x. Let us write x equals 3 on this side. Let's proceed with the variable y. This is equal to determinant of a sub 2 over determinant of a. We copy the matrix A in the denominator. In the numerator, we have the matrix A sub 2. It is similar to our matrix A except the second column is replaced by the constants. Then we evaluate the determinants respectively. In the denominator, we solved this already, so we can just copy the answer here. In the numerator, it becomes like this. 4 plus 4 plus 4 minus 2 minus 4 minus 8. Simplifying the numerator, we will have -2 divided by 2. And the answer is -1. This is the value of y. Let us write here y equals -1. We proceed with the z variable. This is equal to determinant of a sub 3 over determinant of a. We copy the matrix A in the denominator, and the matrix A sub 3 is here. It is similar to matrix A except the third column is replaced by the constants. Then we evaluate the corresponding determinants. In the denominator, again, we solved this a while ago, we just copy the value here. For the numerator, it becomes like this. 4 plus -2 plus -4 minus 4 minus -2 minus -4. The numerator is simplified into 4 minus 2 minus 4 minus 4 plus 2 plus 4. Simplifying now the numerator, it becomes 0. Then we divide by 2. The answer is 0. This is the value of the z. We copy here z equals 0. We are now complete with the values. X equals 3, y equals -1, and z equals 0. I hope you learned something from this video. See you again next time.